Hi, in this session I am going to talk about Bayes' theorem. Bayes' theorem is one of the most important concepts in analytics since several problems are solved using Bayesian statistics. Naive-Bayes algorithm is one of the most popular algorithms used in classification problems such as text classification and sentiment analysis. For example, for two events A and B, we can write two conditional probabilities. Let us say A and B are two events. Then I can write probability of A given B is equal to probability of A intersection B over probability of B. And probability of B given A is again probability of A intersection B divided by probability of A. So, I can rearrange these two formulas. If you look at on the right hand side, I have probability of A intersection B in the numerator. So, this implies your probability of A intersection B is same as probability of A given B times probability of B. So, from this equation again probability of A intersection B is equal to probability of B given A times probability of A. So, here we have left hand side in both these equations we have probability of A intersection B. So, that means your probability of A given B times probability of B is same as probability of B given A times probability of A. So, we have this equation probability of A given B times probability of B is same as probability of B given A times probability of A. I can rearrange this equation and say probability of B given A is same as probability of A given B times probability of B over probability of A. So, this is Bayes' theorem, and it is a very important theorem, and it plays very important role in data science, and also many algorithms are actually based on Bayesian statistics, which in itself is based on Bayes' algorithm. Bayes' theorem helps data scientists to update the probability of an event B when an additional information is provided. This makes Bayesian statistics a very attractive technique since it helps decision makers with fine tuning their beliefs with each additional data received. The following terminologies are used to describe various components in this equation. P of B or the probability of B is the prior probability. So, if you look at this one, this is prior probability. In a way, it is basically a marginal probability without any condition. Then the probability of B given A is the posterior probability. So, here the posterior probability is basically given the event A has occurred, what is the probability of occurrence of B. So, basically what we are trying to do is we are trying to update the prior probability once the event A has occurred. Probability of A given B, which is on the right side of the Bayes' theorem, is the likelihood of observing evidence A if B is true. So, this is likelihood of observing evidence A if B is true, and probability of A is the prior probability of the event A. Let us now understand how Bayes' theorem can be used to solve the Monty Hall problem. Let C1, C2, C3 be the events that the car is behind door 1, 2 and 3. So, basically what I am assuming is that, so we have 3 doors, I am writing D1, D2 and D3. So, I am going to use C1, C2, C3 be the events that the car is behind door 1, 2, 3. So, I am going to write probability of C1, probability of C2 and probability of C3. This is basically the prior probability of finding car behind doors 1, 2 and 3. So, here I am going to say D1, D2, D3. These are the events for Monty opening doors 1, 2 and 3. So, my probability of D1 is what is the probability that Monty will open door 1, and probability of D2 is similarly what is the probability that Monty will open door 2, and P of D3 is probability of Monty opening door 3. Now, let us assume that the player has chosen door 1 and Monty opens door 2. So, that is basically what we are saying is we are assuming that the player has chosen door 1 and Monty has opened door 2. Now, remember the prior probability of finding car behind any of these doors is 1 over 3, equal probability. So, the probability of C1 is same as probability of C2, which is same as probability of C3, which is 1 over 3. Remember, this is the prior probability before Monty opening door 2. Now, let us try to calculate posterior probability. So, here the posterior probability is probability of C1 given D2. So, basically the player has chosen door 1 and Monty has opened door 2. So, basically what we are trying to calculate here is probability of finding car behind door 1 given Monty opened door 2. So, that is basically what we are interested in calculating. Now, we can use Bayes' theorem to calculate this. So, using Bayes' theorem, your probability of C1 given D2, probability of C1 given D2, this is same as probability of D2 given C1 times probability of C1 over probability of D2. So, that is the Bayes' theorem probability, right. Now, let us try to calculate each of these values. So, if you look at probability of C1, that is the prior probability of finding the car behind door 1. So, your probability of C1 is simply 1 over 3. Probability of D2 is prior probability that Monty will open door 2. Remember, there are two doors which are untouched. The door 1 is chosen by the player. That means door 2 and door 3 are available for Monty. So, he can actually choose either of those doors. Remember, this is a prior probability, either of those doors with equal probability. So, your probability of D2 is 1 over 2. Now, let us try to calculate probability of D2 given C1. So, we calculated this part, we calculated that part, we know this part. Now, we have to calculate this particular part of that Bayes equation. So, let us try to understand how we can get that. It is probability of D2 given C1. So, basically what we are trying to do here is what is the probability that if the car is behind door 1, Monty will open door 2. If the car is behind door 1, then door 2 as well as door 3 has GOAT. So, he can use either one of those doors, Monty can use either one of those doors. So, this probability is 1 by 2. Now, let us substitute all these probability values in the Bayes equation. What we will get is probability of C1 given D2, which is probability of D2 given C1 times probability of C1 over probability of D2. Just substitute all those values. What we will get is this is 1 over 2 times 1 over 3 over 1 over 2. So, this gets cancelled. So, we will get 1 over 3. So, basically now the probability of finding car behind door 1 is only 1 over 3. Now, let us try to calculate what will be that probability for door 3. So, let us now calculate what is the probability of finding the car behind door 3 when the door 2 is open. We are interested in finding car behind door 3 when door 2 is open. So, this one again using Bayes' theorem, this is same as probability of D2 given C3 times probability of C3 over probability of D2. So, we already calculated these two prior probabilities, probability of C3 and probability of D2. So, this is 1 over 3, this is 1 over 2, we already calculated that. Now, let us try to understand what is the probability that if the car is behind door 3, Monty will open door 2. Now, that probability is 1. So, probability of D2 given C3 is actually 1. Why is that 1? Remember, the door 1 has been already chosen by the player. Door 3 is where you have car. So, Monty has no other option but to open door 2, right. So, if I substitute here, this probability will become 1 times 1 over 3 over 1 over 2, this is 2 over 3. That means, there is a 2/3 chance of finding the car behind door 3. So, if the player changes his initial choice, then he has higher probability, in fact 2/3 probability of winning the car. Let me now talk about generalization of Bayes' theorem. In this equation, the probability of evidence P of A may come from mutually exclusive subsets of events as described in this figure. For better understanding, consider a pot manufactured by different suppliers such as B1, B2 up to Bn, and let A denote a defective pot. P of A can be written as P of A comma B1 plus P of A comma B2 up to P of A comma Bn. Here P of A comma B1 is nothing but the joint probability between A and B1 or probability of A intersection B1. P of A comma B1 can be written using the conditional probability logic. It is same as probability of A given B1 times probability of B1. Similarly, P of A comma B2 is probability of A given B2 times probability of B2.